Started.
Okay. Okay. Before solving the question of mini quiz, I want to give you an intuition or information with which you can solve the question. Okay. We'll take circuit. Let us say I have this circuit. Input is Vi. This is Vs. I want to know what is VGS and this is RS. And I want to know intuitively what is happening in this circuit. Okay, how will we do it? We'll replace the MOSFET with its small signal equivalent GMVGS from drain to source. This is drain. This source. We have some resistor R, Vi, and RS. Okay, what is the node voltage Vs?
Uh,
Anyone?
GMVGS into RS.
hmm.
GMVGS into RS. And what is VGS in terms of VGS is equals to VI?
Minus GMVGSRS.
Yeah, VGS RS. So I'll bring VGS to this side. Okay, we got VGS as VI by 1 plus GMRS. What happens if GM becomes infinity?
VGS equal to
VGS
0.
becomes zero.
Yeah, that is what there in the question. Everywhere we have to apply the same. Can anyone tell why is this happening? If I remove this resistor RS, will this happen? If I remove this resistor RS, will this happen? If I take out this RS and connect a circuit like
No.
this, in this case VGS is VI. Okay, because of this resistor RS, there is a feedback. We'll check how is this feedback happening. Okay,
We can think this resistor as a current source also. Now we put a current source in place of resistor, then it becomes a negative feedback. Instead of it, there's
yeah,
a resistor.
yeah. We'll see exactly what is happening inside. Let us say I have a same circuit. Some delta V I am applying, and the quiescent current is I. Mm, what is node voltage Vs again?
IRS.
If VI increases, what happens to I?
I increases.
I'm calling it as I instantaneous I plus some delta I. Okay. If II increases, what happens to VS?
VS increases.
Plus VS increases. If VS increases, what happens to VGS?
VGS decreases.
Plus VGS decreases. If
Mm.
VGS decreases, what happens to ID?
ID decreases.
ID decrease.
This is nothing but
Negative feedback.
okay. This register RS is providing you negative feedback inside the system. You can think this as a op amp. You can think this as an ideal op amp with feedback. Okay. Here in our case, GM is infinity. Ideal for ideal op amp, open loop gain A is infinity. So what happens to this node voltage is also becomes Vi. Not, this is nothing but voltage buffer. Here we call it as source follower. Okay, this is clear for everyone.
Uh,
Hello.
Common drain means source follower, no? So it's common drain.
Hey, it depends upon where you apply the input.
Hmm.
Yeah, is it clear for everyone?
Okay,
Okay, now we'll go to the main question. What they have asked is, what is the value of IA by VI? In the circuit, the current flowing, this MOSFET is given as IA. They want the ratio of VI by IA by VI. Okay. From the basic we have seen, if GM is infinity, VGS has to be 0. Okay. In that case, this node potential will be Vi. Everyone agree?
Yes.
So for this MOSFET also, VGS should be 0.
Yes.
So this node potential is 0. Okay. Then the current flowing in this 2 kilo ohm resistor will be 0.
Zero.
Okay. So the current flowing in this MOSFET will be Vi by K, Vi by 1K. This is Vi by 1K. Here it is Vi by 1K. And here it is 0 amps. So this current has to flow through this 3 kilo ohm resistor because the current flowing into the gate is also 0. So Vi by K current will flow through 3 kilo ohm resistor. Hey, someone's mic is on. So I will replace the circuit with the small signal equivalent. Here the current flowing is VI by 1K, and here this GMVS current is nothing but IA, and we have a 4 kilo ohm resistor here. Okay, I'll apply what I have done. Here see KCL. IA is nothing but VI by 1K plus this branch current. No, first of all we have to see why this is 3VI. Yeah, so it is nothing but the current flowing in this way is nothing but, since it is ground, the current flowing is VO2 by 3K. At the same time, this current is equals to VI by 1K. So it turns out that VO2 is 3 times of VI. Is it okay? So from this relation, I can apply KCL here. IA, this IA current is nothing but the current flowing in 3K plus current flowing in 4K resistor. So I have written it as VI by 1K plus 3 VI by 4K. If you simplify this, you will get IA as 1.75 millitimes of VI. What they have asked is IA by VI, which is nothing but 0.00175. Is it clear?
Yes.
Ashadana,
Others,
how
uh,
is three-way how is three-way अक्सर explain చేయమని करना
see from this circuit, the current flowing in 1 kilo ohm resistor, this node potential is VI. The current flowing in this is VI by 1K. Same in 3 kilo ohm resistor. You agree? VI by 1K.
No, voice cut అయింది.
ఇప్పుడు వినపడుతుందా?
ఓకే వినపడుతుంది చెప్పు.
హలో.
వినపడుతుంది చెప్పు.
See, I will tell from starting. The input voltage is VI. They have given GM as infinity. That implies your VGS is 0. That implies VG is Vs. So the node potential here is Vi. So the current flowing in this 1 kilo ohm resistor is Vi by 1K. If you go above, this transistor's Vs should also be 0. This transistor's Vs is tied to 0. So this gate potential will also be 0. Then the current flowing in this 2 kilo ohm resistor will be 0. You agree? So whatever the current flowing in this 1 kilo ohm resistor has to flow in this 3 kilo ohm resistor. There is no other path for that. Okay. So the current flowing in this
ఓకే
3 kilo ohm resistor is Vi by 1K. And this node potential is tied to ground. So from this perspective, if you consider this node as VO2, the current flowing is VO2 by 3K. For you to satisfy KCL, those two currents has to be equal. VO2 by 3K has to be equal to VI by 1K.
ఓకే డన్.
That's why VO2 is 3 times of VI. Okay.
యా అండర్స్టూడ్.
Yeah. Now the current flowing above is IA flowing in the transistor, and the current flowing in this 4K resistor is 3 VI by 4K. and then this 3 kilo ohm resistor is VA by 1K. So if you simplify this, you will get the IA by VA as 0.00175. Okay. And the second part is interesting. They have asked what is IB by VI. Now, since we got this nodal potential as 3 VI, the node potential here will also become 3 VI at the source because VGS is 0. Okay. And for the above transistor also VGS is 0. For this transistor also VGS 0. So this node potential will be at ground. So the current flowing in this 5K resistor is 0. In gate there can't be any current flowing. So the current flowing here also 0 amps. So what is the current flowing in this IB? It is also
Zero.
0 amps. So IB is 0 amps. And the third part they have asked is V naught by VI. So the node potential here is 3 VI, and I'm applying simple KCL here. 3 VI by 6K is nothing but this current. These two are in series because there is no current flowing here. 3 VI by 6K is nothing but V naught minus 3 VI by 7K. You simplify this, you will get V naught by VI as 6.5. Uh, the last thing is R out. What is R out? We'll go to this and solve. We'll solve here for R out. For R out, you should not consider VI grounded. So this node potential is ground. So this will also be 0. The current flowing in is 1 in this 1K is 0 amps. VGF is 0. This is 0. The current flowing in is 2K resistor is also 0. Agree.
So that
Hello.
potential IB will be zero, no?
Yeah, IB will be 0.
Uh,
This VGS is
The
also
PA is
0.
always zero.
Huh? Hello.
so it will become 13K parallel 8K directly.
No, 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 no. That's what. This is important. That's why I'm coming from first stage to the last stage. Okay.
Okay. Okay. RO of the upper MOSFET will also be considered, I guess.
Yeah, yeah, yeah. We'll see. We'll see what is happening.
Yes, yes.
This node potential is also 0. Sorry. The current flowing in this also 0. What is the current flowing in this?
Zero. Zero.
Zero.
And also in IB. Let us say this is V test. The current flowing is I test. Okay. What is this node potential? Anyone?
This view, no?
This node potential.
Oh, this node.
Mm.
Uh, Wait. If this is V test, the gate of the NMOS, no?
Gate of the NMOS, yes.
I 3 VI. It was previously 3 VI, so VI is zero, so
It
that
was
will be
previously 3Y when VA is present. Now what is the node
VI
potential?
is zero, so zero.
Zero, right? So if you apply KCL here, the current flowing in this is zero.
Hmm.
Above it is zero. In this gate also it is zero. So the current flowing in this 3K is
Zero.
Zero.
0 amps. So the potential difference should be 0.
Zero.
That's why it will also be 0
Zero.
volts.
Hmm.
So the current flowing in this is
Zero.
0 amps. Here VGS is 0. That's why this node potential should be
Zero.
Zero.
0 volts. The current coming from here is 0 amps. Agree? IB is 0. Hello.
Yes, yes. IB zero.
Zero, zero, zero. IB zero.
So the current flowing in a 6K resistor is
Zero.
0 amps. From KCL, what should be the current flowing here?
Oh, zero.
It should be 0 amps.
Unless you got the
And
point.
also this node potential is at 0 volts.
Huh.
So the what is the current flowing is nothing but VT by 7K,
Okay.
Huh.
which
It's a
is
good one.
0. That
Zero.
implies VT is
Zero.
Zero.
0 volts. And what is R out? R out is nothing but
VT by
VT
I.
by IT.
VT.
VT
Oh,
zero means
So
IT
R out is
zero.
zero.
0. Okay. Hope everyone got this. Does anyone have any doubts in this? So the crucial thing is to understand this negative feedback and just apply in the above circuit. Just KCL, applying KCL at every point. This is fine. Are there any doubts in this question? Anyone? We go to next question. Hello.
Yes. Yes, Anna.
Yeah. Okay.
Don't uh, sleep, guys. This question will finish 1 15 minutes maybe or 10 minutes. Okay. In this question, they have given these parameters VBC as VTP, and for DC we have to consider lambda as 0, and for AC analysis we have to take lambda as 0.05. So the first question is what is the quiescent voltage at node X? This is node X. we have to find the quiescent potential. And here, if you see, the current flowing here is 100 micro. The current flowing into the gate is
Zero.
0.
0 amps. So the current flowing in M1 is 100 micro.
100 micro.
Yeah, you have W by L, you have mu PCX VTP. You can calculate Vx directly. VSG is given as VTP plus square root of 2ID by mu PCX W by L. If you do this, you will get VGS as VSG as 1 volt. So the potential difference between these 2 points is 1 volt, and this node potential is tied to 3 volts. So the potential at Vx is 2 volts.
2 volts.
Okay. First part is okay, I think. Simple. And the second part is what is the quiescent current flowing through 5 kilo ohm resistor in amperes? How will you calculate that? The key point here you should take is while doing DC analysis, should open circuit this small signal current source. Then the current flowing in gate is 0 amps.
Uh,
The current flowing in this open circuit is 0 amps. So the current flowing in 5 kilo ohm resistor is
0 amps.
0 amps.
0 amps.
Next one is what is the quiescent voltage at node Y in volts? For that, here 10 microamps is flowing in M node and W by L is 10 times. So the current flowing in M2 will be 100 microamps. So from that, you can calculate VSG of M3. You can calculate VSG of M3. See, this formula you should remember every time. In exam, you can't go and plug ID is equals to half mu PCX W by L VSG minus VT whole square, and then you take out the relation for VSG. It is not recommended. In 50 minutes exam, it is not possible to derive all these things. And if you do like that, you won't get time. You will get less marks. So you should remember t plus square root of 2id by mu PCS W by L. You plug the values, VSG will turn to be 0.9 volts. So in the previous uh, question number 3, we got current flowing in 5 kilo ohm resistor as 0 amps. For that to happen, no potential difference should be there across 5 kilo ohm resistor. That means that this node potential is 2 volts. And we got VSG of M3 as 0.9 volts. That implies Vy is
1.9.
1.1 volt. And the fourth part is what is the trans impedance V naught by Ia? For that, you apply a small signal analysis. The current flowing from drain to source is GMVGS, and you have a resistor from drain to source R01. You have a current source connected to this 5 kilo ohm resistor. and here you have two MOSFETs, and their R naught will be in parallel. R naught 2 parallel R naught 3 will be connected to 5K to ground. R naught 2 parallel R naught 3, and drain to source as usual. GM to VGS2, drain to source GM VGS. The key thing is mm, in small signal analysis. Hello,
Yes.
Yeah, వినబడుతుంది.
where did it got cut?
Small signal
స్మాల్ సిగ్నల్ అనాలిసిస్ అన్నావు అక్కడ.
Small signal analysis. This part you didn't listen, huh?
నో
Advanced
అన్నా,
PMOS.
నో అన్నా.
Okay, okay. I will tell again. So to take NMOS, current will flow from drain to source. Okay. Small signal analysis also, while you represent this, you will draw a current source from drain to source. The current source value will be GM VGS. Okay. While in PMOS, the current will flow from source to drain. In small signal, you will represent the same, and you will the current value will be GM times VSG from source to drain. So the current flowing from drain to source is GM times VGS. So you should be careful about this. When you apply GM VGS for PMOS also, it should be GM VGS, not GM VSG. If you do GM VSG, the direction of current source should be from source to drain. If you do GM VGS, it should be from drain to source. Okay. Hello.
Okay.
Hello, anyone? Hmm. So for the above circuit, I have drawn small signal equivalent here. And if you see, there will be no current flowing in this gate. Okay. So this node potential will be at 0. So this current will go to 0 amps. So what is the current flowing in this 5K resistor? If I call it as V1, V1, hello,
V1 minus V0
yeah. So this voltage drop is V0 minus V1, and the current flowing in this 5K is IA. So V0 minus V1 is IA times 5K. So I can write V1 as V0 minus 5K times IA. And for the above transistor, if you see
What is
here,
V1?
just a node potential. I have given one name, just node potential as at this point.
Okay. Okay.
Hmm. And the source is tied to ground here for this transistor, and this is gate of the transistor. For this, VGS1 will be V1. V1 is
Okay.
nothing but V0 minus 5K times IA. This node potential VG3 is minus GM VGS1 into R1. Minus GM VGS1 current will flow in this direction. And this node potential is nothing but minus GM VGS1 into R1. And VGS1 is nothing but VG VGS is nothing but VS1 is nothing but V1. V1 is V0 minus 5K IA. Substitute this, you will get this. And VGS3 is nothing but VG3 minus VS3. VS3 is nothing but V0. That is some simple simplification. If you do this, you will get VA by IA as 5000. Because the small signal analysis part and this calculation are far apart, I'm not able to go back and forth. So it is just simplification you can check out.
So one thing I noticed while you draw a PMOS small signal, you take RO to the lower side. So it makes the diagram more clean. Actually, I
Yeah,
usually make it on the upside only. So I usually get confused while drawing the small signal of PMOS. If there are 3 to 4 PMOS, yeah, but
yes. See, way I made this way is, see, here I'll tell you. This is PMOS. If I take this R naught here, I can find out this node potential from the above current, from this current. I will know this potential clearly, and this potential is going to affect the current flowing in this MOSFET. Okay, in that
Yes.
way I can see the VGS clearly. I'll, if required, I name it as G3 also. I will write it down. If you see also, I'll write it down. What is what? This is G1. This VG3, gate of transistor 3. This VS3. You can initially you can write down if you have confusion. There is no problem. This one time job, right? If you don't do it, if you mess up, your whole question will go. See here, I have written this as G2. It makes the problem clear to you. You can solve it quickly
Hmm.
with no confusion. Similarly, for output resistance, what I have done is I have applied a voltage same small signal circuit, and if you see here,
This is open, this is open, this is open.
I apply voltage at this point for finding output resistance. This current source will be open. Current flowing in this gate will be zero. So
Zero,
the current flowing in this 5K is also zero.
zero.
So this node potential will also become VT. That's what I have written here. This node potential will also become VT, and this is nothing but gate of transistor M1. VGS1 is nothing but VT because source is tied to ground. So this VGS is VT. So the current flowing is GMVT. So the potential at this node potential is VG3 is nothing but the current flowing this way is minus GM1 VT. So the potential is minus GM VT times RO1, and this node potential is going to affect the VGS of this transistor. So VGS3 is nothing but VG3 minus VS3. So I have written it directly. VG3 is minus VT times, because this is also VT, becomes minus VT times 1 plus GM or not. And I have applied KCL here to find the current. You take it this way. Uh, GM3 VGS3 RO2 parallel RO3 and VT IT. So IT will be sum of these two currents. VT by RO2 parallel RO3 plus GM3 VGS3. This minus minus sign will go. The current flowing in this direction will be minus GM VGS3. So the minus minus will cancel. So it will be GM VT3 times 1 plus GM1 RO1. If you put those values, you will get VT by IT as 2.48. Answer is 2.5. So thought I will discuss this, but I haven't done it fully. So we'll see next time, or we'll see in lab.
Yes. Yes.
Okay. Okay.
That is previous year made this paper, right?
Yes, yes, that was previous mid paper.
Okay, okay.
You can stop recording.